In past videos, you've heard me talk about dependence, that we want to understand the dependence that exists in the time series and use that to predict values in the time series, and then also eventually to forecast future possible values that can occur. So now this particular subsection of our notes starts talking about, well, how can we measure in a formal manner the dependence? Now, if we want to have a full, complete understanding of the dependence that exists between our random variables, we would need to understand what the joint distribution function is for these corresponding random variables in our time series. Unfortunately, this can be quite difficult. And you might be thinking, well, wait a second, I've been talking about, or you've been seeing joint probability distributions in other courses before. And in fact, after all, a likelihood function is typically defined in terms of a full joint probability distribution for your random variables. The problem, though, is that in typically the most likelihood function settings, you're assuming independence between your observed values. So that, let's say if I have a joint probability distribution function x1 through xn, independence will allow me to simply write it like this, as the product of the marginal PDFs. We can't do that here because we now do have dependence between our time series, or our random variables in our time series. And so this makes getting at that joint probability distribution function much, much more difficult. So we won't completely be able to understand all the kinds of dependence that exists. But what we will do is try to simplify the problem, and so that we can get an idea of what the dependent structure is. Now, to begin with here, so that we can get to the dependence part of this section, we need to first look at stuff in, let's say, one dimension, meaning one random variable at a time. In other words, using the marginal probability distribution for, let's say, x sub t. And so, here's our marginal probability distribution function, denoted as f sub t of x, to say, okay, this is what the PDF is for x of t. We could also define then the joint CDF as well. These concepts should not be new. And once we have these, then we can find, well, what would be the mean value function corresponding to x of t. And so we can denote that as mu sub x of t to, again, designate, well, which random variable are we talking about? We're talking about x of t as a general manner from t equal 1 to n. This is just simply the expected value of x of t, and you will use usual, if we have a continuous probability distribution, use the usual methods to find what that expected value would be. Now, very often, there's not going to be, that you're working with, let's say, the variable x, and if that's the case, then we could just simply drop the x part from the subscript for mu and just deal with mu sub t. There will be other situations where we have maybe more than one variable that we're talking about, more than one time series. In that case, then we can use, let's say, mu sub xt, or mu sub yt, mu sub wt, and so on. Okay, so the concept of an expected value of a random variable is not new. But in the context of, well, what we are doing here, what exactly does mu sub t mean? Because if we, like, for example, think of the OSU enrollment data, we just can't observe only one possible time series. So what does it mean for a mu, which you typically think of as the average of all possible values for x in a population setting? What does that mean now in a time series context? And here are two different ways to think about this. Mu sub t represents the mean taken over all possible events that could have produced x sub t. In other words, let's say all possible events that could have produced the OSU enrollment for a particular semester. That's one way to think about that. Another way to think about what mu sub t represents, and this wouldn't work for the OSU enrollment, but it would work in other settings, is that suppose that x1 through xn, our time series, is observed an infinite number of times. So you could imagine, let's say, maybe some kind of manufacturing process where you could, let's say, maybe repeat observing a particular time series concerning that manufacturing process. You could maybe conceivably observe it many, many, many times. So in that particular setting, then we can think of mu1 representing the average value at time 1, mu sub 2 representing the average value at time 2, mu sub t is the average value at time t. Okay, so let's take a look at an example how to find mu sub t. And so we're going to go back to this moving average example that we've looked at before. This is a 3-point moving average that we're working with here. What would mu sub t be in this particular setting? Note that these WTs are independent normal 0, 1s. So to find this, we use some basic ideas of how to find or how to work with expectations. So, for example, in another class, in a mathematical statistics class, suppose that you had a random variable y and also have a constant a. In that class, you learn that the expected value of a times y is equal to a times expected value of y. So we can simply just factor out the constant from the expectation. Also, let's say if I have random variables y1 and y2, not necessarily in terms of a time series, but just different random variables, and also I have constants a1 and a2. What you also learn is that if I were to take the expected value of a1 times y1 plus a2 y2, what we can do is we can bring that expectation within inside the sum like this. Okay? These are some basic concepts that are taught in a mathematical statistics course. Now, using these concepts, then let's go back and find that the mean of that moving average. Let me do some erasing here. Okay. So I want to find mu sub t, which is the expected value of m sub t. So the first thing that we do, let's call it step 1, we put in what m sub t is. Then we can see that we do have that constant in there because we're always dividing by 3. So step 2, then I factor that constant out. Step 3, then I bring my expectation through the sum. And we know what each of these individual expectations are because WT has an expected value or mean of 0. So each of these expected values in step 4 become zeros, and then mu sub t overall is equal to 0. Okay, so that wasn't too difficult to find. Let's take a look at another example. This goes back to our autoregression example that we saw earlier. In that particular model, we had x of t is equal to 0.7 times x of t minus 1. So we go back one time period plus WT, where WT was again independent, identically distributed, normal 0 and 1. Then, step 1, we write what mu sub t is. It's equal to the expected value of t. Step 2, we put in, well, what is x of t? Step 3, we're going to bring that expectation through. Perhaps if I wanted to do this step by step, I would have done something like this. I bring that expectation through the sum. Step 3, then, I factor out my constant from x of t, from that expectation. Then step 4, well, what is expected value of t? WT? Well, it's equal to 0, because what we have up there. And then, well, what is then x of t minus 1? Well, using the definition of what our model is, I can now start writing this as 0.7 times x of t minus 2 plus wt minus 1. Well, using the same concepts then with that expected value, we can write this as 0.7 times expected value of xt minus 2 plus wt minus 1. Oops, expected value of wt minus 1. This becomes 0. Then we can again plug in what x of t minus 2 is, and you can see a pattern that's going to form. That simply we're going to have 0.7 times 0.7 times 0.7 times 0.7. I'm running out of room. X of t minus something there, and then everything else is equal to 0. These 0.7s, when I keep on multiplying them together, they're going to get smaller and smaller and smaller, and eventually you can say that mu sub t is equal to 0. Now, I did leave out some formality there. You know, you might be thinking, okay, well, is this equal to 0 in terms of the limit? We'll get to this more a little bit later in the course, but I think you can at least agree with me that, yeah, it looks like everything's going to 0 there. Okay, so now we've defined the mean function itself. That's not going to tell us about dependence, but what this is going to do is we're going to use that in how we're going to measure dependence in this next little part here. Okay, so in another class, in a mathematical statistics course, you've talked about the covariance between two random variables. That this measures the amount of linear dependence that exists between these two random variables. And so in a non-time series context, let's say I have two random variables, x and y. The covariance for x and y is defined as the expected value of x minus mu sub x, where mu sub x is the expected value of x, times y minus mu sub y, where mu sub y is the expected value of y. We can then simplify this as expected value of x times y minus mu sub x times mu sub y. Basic definition of covariance. Of course, if we have a covariance of 0, that means that we have no dependence between x and y, or at least no linear dependence between x and y. If this is positive, it means that we have positive association between x and y, meaning as x increases, y tends to increase as well, and vice versa. If the covariance is negative, that says we have negative dependence between x and y, meaning as x increases, y tends to decrease, and so on. Now, we are going to use the same idea of covariance to define what's called the autocovariance function for a time series set of random variables. Again, the word auto there is because we are finding the covariance for the same, essentially the same variable itself, but at different time points. So let's say we're interested in two different time points, S and T. In a symbolic form, we define the autocovariance function as gamma. We put a subscript x there corresponding to the variable of interest. And then in parentheses, we put in the two different time points. Again, to be very general, we're going to have S and T as the two different time points. And all this is simply the covariance between x sub S and x sub T. Then I can write out then using the usual definition of what covariance represents. So we have the expected value of x sub S minus its corresponding mean times x of t minus its corresponding mean. And as long as we have a continuous distribution for x of s and x of t, we could write it out in terms of an integral format there. So some notes. If the autocovariance is equal to 0, that means, of course, then there's no linear dependence. If s was equal to t, then that means I have a t here, I have a t here, and notice I'm going to have two of these x of t minus mu sub t's. So in other words, I have just the regular old variance for x of t. And if there's no confusion about which random variables you're working with, or I should say, well, which variable that you're working with, in terms of, you have an x, do you have a y, we can just simply drop the subscript on the gamma and just go with that. Okay, so let's take a look at an example. So let's talk about white noise once again. White noise is basically, let's say W sub t is distributed independent, identically distributed with mean of 0, variance of sigma squared W. You don't have to have the normal there for this part, but suppose it has a normal distribution. Well, what is gamma of s of t? Well, in this particular setting, because of this independence, then that means each of the WTs are independent. So for example, W1 is independent of W2. So when the subscripts do not match for the two random variables that you're looking at, then the corresponding autocovariance function would be equal to 0. Now when the subscripts do match, now you're in a variance. You have a variance. So that variance would be sigma squared W. Okay, so that obviously is quite easy. Now let's take a look at the moving average though. Remember when we first looked at a moving average, I said, well, okay, now this is going to introduce some dependence between successive, or between perhaps any of the particular values in our time series itself. And indeed, that's what's going to happen here. And so what we're going to do here is do a proof of what the corresponding autocovariance function would be for this 3-point moving average. You're going to see a lot of these proofs in our class, and you will be responsible for doing many of these proofs in our class as well. Okay, so let's take this step by step. Here's the definition of what my autocovariance function is in the context of these moving averages. Now, we just showed that mu sub t, or the mean, is equal to 0 for all possible values of t. So now our autocovariance function just simply ends up being the expected value of m sub s times m sub t. So let's write this out. Here would be m sub s. Here's m sub t. Notice how I have a constant in there. I have a 1/3 times a 1/3. So I can factor that out. And now I need to find, well, what's the expected value of the stuff that's in the middle? And that expected value is dependent upon how close is s to t. So let's look at one setting. Suppose s is equal to t. So I have exactly the same time point. Then the expected value of the expected value of m sub s times m sub t becomes just the expected value of m sub t squared. And then I can use the definition of what a variance is. The variance of m sub t would be the expected value of m sub t squared, that second moment, minus the expected value of m sub t, that quantity squared, so the first moment squared. And so I can basically reverse that. Whoops. And so that now the expected value of m sub t squared is equal to the variance of m sub t plus the expected value of m sub t, that quantity squared. Okay. We know that this expected value is equal to 0 because we just proved that. What we don't know yet is what this variance is. So let's write this out. let's write out what m sub t is. Well, it's wt plus wt minus 1 plus wt minus 2, that quantity divided by 1/3. Then again, using properties of variances. Again, suppose I have a constant a, I have a random variable y. This is equal to, if I want to find the variance of a times y, this is equal to a squared times the variance of y. So I can factor out that 1/3 that would be in the moving average. It's factored out as 1/9. And now I have the variance of wt plus wt minus 1 plus wt minus 2. Okay. Now, something else that you would have learned in a mathematical statistics class is if, let's say, if I have two independent random variables, let's call it y1 and y2, and I want to find the variance of their sum. If they're independent, then I can simply move that variance through the sum like this. And so essentially that's what we have in this particular setting. These w's, since they're white noise, are all independent, so I can move that variance through the sum, as we see here. And if we go back up to, well, how was this wt defined? Wt had a variance of 1. So each of these variances become 1s, and so I'm left with then 3/9 or 1/3 as then what the autocovariance function would be when s is equal to t. Okay, let's do one more of these. Suppose now that s is equal to t minus 1, so we're going one time period into the past from where t is itself. To find the autocovariance, then I need to find, well, the expected value of m sub t minus 1 times m sub t. So what I do is I write out what m sub t minus 1 would be, and also m sub t. Each of them have a divided by 1/3 with them, or divided by 3 with them, and so I can factor out that, and so that's why I have this 1/9 out in front. Now, to find this particular expectation, I need to multiply everything out. And so let's say this is step 1. Step 2, I multiply everything out within those brackets. Then step 3, I distribute the expectation within the sum. Step 4, I look to simplify a little bit here. Notice how I have some subscripts that are exactly the same on some of these random variables. So that means, for example, I have 2 of these w sub t minus 1s. So in other words, since I'm multiplying, I have w sub t minus 1 squared. And so we see that occur here. We see that occur right there. Okay. Also, in step 4 here, I have this situation here, where I have an expected value of this w sub t minus 1 times w sub t. Now, in a mathematical statistics course, let's say if you have 2 random variables, y1 and y2, that are independent, and I want to find the expected value of y1 times y2. If they're independent, then I can move that expectation through the product. This is only occurs when you have, again, independent random variables. And so what I do then over here for the white noise, the w sub t's, I can move that expectation through the product and get that. And in fact, you can see that this actually occurs a lot through all the terms that I have here. Each of these expected values, well, what are they? Well, we go back up here. We know that these WTs have a mean of 0. So I'm going to have a whole bunch of zeros that pop up. Expected value of w sub t minus 1, 0. Expected value of wt is equal to 0, and so on. And then the expected value of w sub t squared, or expected value of wt minus 1 squared. remember what that is. That would be equal to the variance of Wt minus 1 plus expected value of Wt minus 1, that quantity squared. We know that this expected value is 0. We also know the variance is equal to 1. So then this expected value is equal to 1. Okay. So if you go through the math, you're going to see just 2 1s that pop up. And so my overall autocovariance then happens to be 2 9ths. Well, what if, let's say, s is equal to t minus 2? Well, I'll let you look at that on your own. It just uses the same concepts that we just did with t minus 1, and we end up getting 1 9th. Well, what about now t minus 3? That 3 is a key here. Remember, we have a 3-point moving average. So we get to the point, let's say, where now when we look at m sub t minus 3 and then also m sub t, notice that these subscripts here are never the same. And so what ends up happening then is that I'm going to have a bunch of expected values that end up being equal to 0, and overall my autocovariance function is 0. And hopefully that makes some intuitive sense that if my moving average looks at 3 time points in it, if I want to find the dependence outside of those 3 time points, well, there isn't any. Now, one could also do this kind of a proof using t plus 1, t plus 2 as s as well, and everything's going to follow in a similar manner. And you could go t minus 4, t minus 5, and so on. And after you do all that, this is what you get then for the autocovariance function. So when the subscripts are the same, so you're dealing with the same random variable, you get 3 9ths. When they are 1 time period apart, like maybe 1 and 2, or let's say 10 and 11, you get an autocovariance of equal to 2 9ths. If they're 2 time periods apart, you get an autocovariance of 1 9th. And then when you are 3 or more time periods apart, you get 0 for the autocovariance. So the number of time points that you're apart, so the absolute value of s minus t, that has a very special name in time series analysis. This is referred to as a lag. We will use that terminology a lot. So at lag 1, the autocovariance function is 2 9ths. At lag 2, the autocovariance function is 1 9th. For lags 3 or more, I have an autocovariance function of 0. Excuse me. And what's interesting also for this particular example is that the autocovariance here depends upon the lag, but not the individual times for the moving average. So it doesn't matter if I'm looking at, let's say, x of 3 and x of 5, or maybe let's say x of 10 and x of 12, I get exactly the same autocovariance. It's the difference between these subscripts, the lag, that's important. This will be as I have here, a very, very important concept to understand as we go along in this semester. Okay. Now, in another class, when you've talked about the covariance, the covariance is a nice measure of the linear dependence between 2 random variables. But there is one problem with it. And that is there's not necessarily an upper bound for what the value can be for for a covariance. There's not a lower bound. And so instead what you typically work with is what's called the Pearson correlation coefficient. So if I have simply just 2 random variables, x and y, none in time series context, the Pearson correlation coefficient. Rho is the covariance between x and y divided by the square root of the variance of x times the square root of the variance of y. And the nice thing about this particular this quantity here, the Pearson correlation coefficient, is that this quantity is always between -1 and 1. So the closer you get to +1, the stronger the dependence that exists between x and y. The closer you get to -1, the stronger the negative dependence that exists between x and y. The closer you get to 0, the less there is in terms of dependence between x and y. Now, in a time series context, we are going to look at the autocorrelation instead. I shouldn't say instead, because it's basically the same concept. It's just a correlation, but now is for the same variable of interest, but we're going to look at it at, let's say, 2 different time points. And so the autocorrelation function, or ACF for short, something that we're going to use throughout the rest of this course, is simply defined as follows. The autocorrelation, we're going to use the Greek letter rho, and we need to put the corresponding time points with it, so s and t, to be very general. It's equal to the autocovariance function at s and t divided by the square root of the variance at time point s times the square root of the variance at time point t. This ACF is still defined to be between -1 and +1. It is a similar interpretation as a correlation coefficient. So, a very simple example for white noise. Well, what is then the corresponding ACF for it? Well, remember, of course, this independence then means that the correlation then is equal to 0 for s not equal to t. If we have s equal to t, then that correlation is 1 because you have just the same value. Well, what about now this moving average? Obviously, this is a little bit more difficult. Well, what we just found a few minutes ago was the autocovariance function. And so we can take this autocovariance function and simply find then the autocorrelation function with it. So for example, when we are at a lag of 1, that means then the autocovariance is 2/9. And we need to divide it by then what the variance, we need to divide it by what the variance is at, let's say, time s, square root that, and divide by the variance at time t, square root that. Well, it doesn't matter if s is equal to 1, 2, 3, or 4, t is equal to 1, 2, 3, or 4. I'm always going to have 3/9 then as that variance. And so if you go through all the math then, the autocorrelation function ends up being 2/3 at a lag of 1. On your own, make sure you can verify these other autocorrelation values as well. So, put into a context that all of us are used to in terms of a Pearson correlation coefficient, we can see at lag 1, we have somewhat strong, moderate to strong dependence. At lag 2, we have some dependence. It's a positive dependence. We have some positive dependence there, but it's not necessarily too strong. And then once we get beyond, once we're at lag 3 or beyond, we have no dependence at all. And again, think of that in an intuitive concept, or think of that from an intuitive point of view, that I have a 3-point moving average. Once I get 3 or more points in terms of the difference in how that m sub t is found at 2 successive time points, then I have no linear dependence between the two because they don't share any of the same WTs in their formulation. That's why I have a value of 0 there. Okay, so let's take a look at another example. This helps you now see what dependence looks like if I were to plot a time series. Now, all of you should have a general understanding of what dependence looks like in a scatter plot. So if I had, let's say, this is outside a time series context. Let's say I have variable x, I have a variable y. And let's say that the correlation is, let's say, close to 1. And I take a sample from my population, I would have something like this. You know, I had the points kind of tightly clustered together. They form a strong linear trend that goes up in that plot. That's what it would look like if I had if I had strong positive dependence. If I had negative dependence, then I would strong negative dependence. Let's say something kind of close to -1, I would have that. If I have, let's say, little dependence at all, let me get my eraser out. Then I would have just a scattering of points here, and they're not necessarily forming any particular kind of trend. Okay, but now in a time series context, then, you know, what does this actually mean? Let me continue erasing here. Because what we're interested in is plotting the data over time. What does strong positive dependence look like? What does strong negative dependence look like? What does really no dependence look like? And so here's a fill in the blank question then to help you see where we're going with this. If there is strong positive linear dependence between x of s and x of t, the time series will either appear smooth or choppy in a plot of the series versus time. Choose one answer. So why don't you pause this video here and think about, you know, if I have strong linear dependence, what would this actually look like? Is it smooth or a choppy? So what does smooth or choppy mean? Well, let me go ahead and do this. T, x of t. So smooth might be more something like this, where we kind of go up and down, maybe over time. Here are my time points as well. Where a choppy, I think I sometimes use the term lots of oscillation in the past. It might be something like this, where we see a lot of movement in the series relative to where the points are. So, pause this video and think about it. What would you expect this time series to look like if you had strong positive dependence? The answer is smooth. And the reason being is because think about what, let's say, dependence close to a positive 1 actually means. That means you're going to have, when you have, let's say, large values, when you have a large observed value, you would expect then the next observed value to be also large because you have strong positive dependence. And so because of that, then, you know, these trends here that you're going to see in this plot tend to go up for a while in terms of the points, then go down, and so on. You're going to have similar values that are observed in that time series for points that are close to one another in terms of the lag. Then let's say if I have strong negative linear dependence between x of s and x of t, you know, would the time series plot be smooth or choppy? And the answer is choppy. Again, think about what dependence in this kind of a concept, in this kind of a setting means. If I have, let's say, a large value, let's say maybe at x of 2, I have a large value for my time series. If I have negative dependence at x of 3 with x of 2, well then, basically what's happening at x of 2 is going in a different direction than what's happening for x of 3. And so what will happen is if I have a strong positive value, a large value at x of 2, I'm going to likely have a small value at x of 3 because the dependence is going in an opposite direction. Okay, so let's take a look at some plots to help illustrate this. On your own, take a look at my corresponding program that's going to produce these plots. I'm not going to go through the code here on this video. And let's say that I have kind of a moderate amount of dependence. So for this particular setting, I happen to know what the autocorrelation function is for one lag. And if we just look at one lag, that would be sufficient for what we're doing here. The autocorrelation is 0.5. I will tell you for other lags, it's going to dramatically drop close to 0. So I have a positive autocorrelation. And what you'll learn about later in the semester about how you can estimate what that is based upon some data. And the estimate's close to what the actual, the true value is. And this is what we get. So what we see here is that, we tend to have, large values kind of sticking together. And then eventually, maybe small values sticking together as well on this plot. I mean, it's not perfect. Remember this, I can't erase that for some reason. Let me get my eraser out. Now, this is not perfect positive dependence. No, we're at about 0.5. But what we see here is we tend to see some kind of trends that, again, large values tend to stick together for a while in the plot. Small values tend to stick together for a while in the plot, and so on. And so now if we take a look at a different setting, well, actually, let me first of all, we could take a look at this. So for a one lag difference between the values in the time series, we could see what you would normally think of often introduced, like for example in a regression course, that we do have an upward trend on this plot, but it's not necessarily a strong upward trend. We have, again, large values relative to x tend to stick together. Small values tend to stick together as well. If you're in the middle, you tend to stick together as well for the two different variables. Now, let's say that I have now negative dependence. So the same amount of dependence, but now in terms of a negative sense. Compare this plot to what we just had. Notice how much more choppy the points are. So notice I'm here, I go up. Now I go back down. I go back up. I go back down again, and so on. So we have this choppiness, and that's because now we have this negative dependence that occurs. So this plot looks dramatically different from the one that we just saw. Then if we have a particular setting where we have no linear dependence, now we see a plot that's somewhat in between the previous two plots. So this just summarizes what I said here. So you can see then, in terms of the big picture, what we're going to be doing in this class. We can see how dependence then can affect how you make predictions about what our time series values will be, and also you can think about what future values, forecasted values would be in the time series. So if I come back up to when we have positive dependence, if I have positive dependence, then I'm more likely to think that, let's say, the next value, so I have 100 different values here, the value at 101 might be, let's say, maybe somewhere around there when I have positive dependence. When I have negative dependence, at time point 101, time point 100, I'm there. For time point 101, I'd probably be down there instead. And so this is, again, how we're going to use this dependence to help form a time series model that formally will allow us to forecast future values. So with that then, that's the end of this little subsection on dependence.